this picture and approach, and kind of much less about any of the details, but feel free to ask at any point. I guess my general motivation for this, so as mentioned earlier in this conference, first of all, when we have, so we have in the global setting, like Shida, so it's that if we have two number fields, then there's a fundamental group or their absolute Galois group, gives us an isomorphism between the fields, and in fact we have that all group theoretic outer automorphisms are in bijection with field isomorphisms between the two fields, and kind of in particular, and in corollary of this, is the absolute Galois group of Q has no outer automorphisms. The automorphism is inner, but then in the local setting, Michizuki and show the following. So if we have K1 and K2, some finite extensions of QT, and throughout my talk, I will put the not equal to 2, because right now it's necessarily needed. Then we have kind of something similar, that the absolute Galois groups have some bijection with the isomorphisms of the fields. But now we need some extra information about the ramification filtration being preserved. And part of the proof goes through using the fact that the filtration is preserved to show that a certain Hodge-Tate representation goes to a Hodge-Tate representation when we act on it by precomposition with this outer automorphism. And this is used to show that the outer automorphism comes from geometry, so from some field isomorphism. And I guess the original question, which I'm very interested in understanding, is, well, if we remove the ramification filtration, so if we have some outer automorphism of the Galois group, what does it do to representations? How does it act on the space? What does it do to take representations? And kind of more explicitly, I was also interested in, for example, in the book Cohomology of Number Fields. It was a specific example is given, which I will later mention in more details. But they constructed a very specific outer automorphism. And I guess question kind of, can I take a specific V and look at the orbit and describe the orbit under this specific outer automorphism?
So, NSW.
Neukirch-Schmidt-Ringberg cohomology of numbers.
It wasn't because you said cohomology of number fields and you wrote
Yes, sorry.
NSWs.
Yes, sorry. I'm in the book Neukirch, Schmidt and Winkler. And I guess one can ask, for example, well, will all these powers be even like non-trivial outer automorphisms? And kind of even that wasn't really clear from the construction. And it was shown by Hoshi and Misho in 2022. That if we take an actual extension of QP, then this phi has phi to the n is non-trivial as an outer automorphism. For every non-zero integer.
You mean the phi constructed in NSW?
Yes, phi and one more thing which can be said, that's what we showed, that any kind of psi out of GK is geometric, so comes from an isomorphism of the field. If and only if psi is both Hodge state preserving. So that means sends every Hodge state to Hodge state. So from this, we kind of get that if we have ones which don't come from geometry, they should have some non-trivial action on Hodge state, and that's kind of my main motivation. I don't have too much to say about this, but what I do have to say is, well, one of the problems is there aren't that many examples of what this outer automorphism group is, and like I said, until recently, it wasn't even known if it's infinite. So this outer automorphism kind of should look like a Dehn twist, and I'll kind of try and explain why and how it can actually be seen in a uniform way with Dehn twists. So kind of led me to this approach is this ideas of Kapranov, Reznikov, Mazer, and Morishita in arithmetic topology. And the idea there is that number fields behave in similar way to low-dimensional topology. And so I'll just kind of quickly sketch some of the ideas there, but if now so this is some number field. And on the topological side, this corresponds to a three-manifold. Then it's kind of thought as the Briggs sphere. And under this analogy, Neukirch is thought of as some sort of Musto rigidity, which says that for hyperbolic three manifolds, their fundamental group determines the manifold. But I'll kind of say in a minute why it's not exactly. And then a prime number sitting inside of type of OK corresponds to a knot K. And so then if you look at this should correspond to a linked group. So I1 of the manifold M raise the knot. So kind of from this point of view, at least, most of rigidity should correspond actually to having some Neukirch theta for a finite set of primes S. But also it has this extra thing about hyperbolicity. But kind of in the local setting, what do you get? You get that O of the completion of the prime is some tubular neighborhood of the knot. The p-adic field, at least classically, is kind of thought as this torus, but kind of one issue that arises from this is this only accounts to the tame part of the Galois group of the p-adic field, partially because, well, here you're only considering tamely ramified coverings of the manifold, what is wild ramified for a topological manifold. But kind of I suggest another way of kind of thinking of p-adic fields, and that is the following. So from now on, yeah, suppose that there are some p roots of unity inside of K, some finite extension of QP, and actually it has p to the s roots of unity, but not p to the s plus 1, and Kp over Qp has degree n. So this should kind of correspond to a genus n divided by 2 plus 1 surface, which is only oriented mode p to the s. So in a certain sense, it kind of acts like something with a non-oriented thing outside of it and oriented mod p to the s. And now looking at this, when I want to study the outer automorphism of the Galois group, then what is outer automorphisms of I1 of the surface? Well, by the Dehn-Nielsen-Baer theorem, this is the same as studying the Mathematisches class group of this surface, which is just homeomorphisms up to isotopy. And these objects, mapping class group, are very well studied. A lot of the structure is known. So, for example, these are generated by 2G plus 1 Dehn. And also, in terms of the question about representation, well, the mapping class group has a nice action on spaces of representation of I1S. For example, one very nice space is the Teichmuller space of it, which looks at all the complex structures on the surface. And this thing is the same as the connected component of from I1 of S to PSL R mod conjugation by PSL to R. And so this the mapping class group acts on it and has ergodic mixing, so action. So I guess the kind of big hope would be to get some sort of nice dynamics on spaces of representations of Nadav groups of chaotic fields. But to understand this mapping class group,
I'm confused. Aren't the orbits of the mapping class group on Teichmuller space like more or less discrete? The quotient is mg. I'm confused with the claim that it's ergodic.
actions. Maybe I'm confused then.
Well, we can,
Yeah, we can discuss.
Probably.
Pretty sure there are some like,
Yeah, I think if you put an SU in there, it would be ergodic.
yeah, maybe to higher Teichmuller. Yes, sorry. Discuss this later, but the action is well understood and but I guess the first step would be to understand, well, what are Dehn twists to generate the mapping class group. Kind of let you mind. So for a Dehn twist, you need some simple closed curve alpha on your surface, and you take some tubular neighborhood of the curve, you cut it out, and then on that tube, what it does is it twists it around once, and so this would kind of give us P of alpha, say on beta, we'll send this going around and back. So it twists it once around where alpha was. Well, okay, now that we have a p-adic field, then what is a simple closed curve on a p-adic field? To do this, I will first start with the discrete world and give some with looking at simple closed curves on just a general group. And what do I mean by that? Well, one fact is that, well, every simple closed curve on S gives Z splitting of I1 of S, and by that I mean that either I1 of S can be written as a amalgamated free product with B, or this is equal to some agent and extension. So amalgamated free products will correspond to a simple closed curve when you erase it having two connected components, and it's just by Wittgenstein, and this is if you get one connected component. or in this case, the thing generated by A and B with the extra relation. We have a map here, phi1, and a map here, phi2. Then we want phi1. And phi2. 1. And here this would be if you would need two maps from Z into A. And so then this would be generated by A, some extra letter T, and the relation that phi1 Z is equal to B by 2 of Z and the inverse. And so given such a Z splitting, one can also, well, oh yeah, and any such splitting comes from a simple closed curve. So actually looking at all ways to split over Z for a pi1 of S would be exactly like looking at all simple closed curves. Using my guide, one tool to using the language of graphs of groups, and one can also look at multi-curves, so a family of curves which don't intersect. And so instead I kind of the way to look at curves on, I will now take the maximum appropriate quotient on the Galois group of a field, and these will be all the key splittings of the group. So this would be with phi1 as the more big to my given group B. I'm not going to go into the theory of graphs of groups.
G2 is the maximum quotient.
Yes. So I'm not going to go into the theory of graphs of groups, but basically it's just doing iterated amalgamations and agent and extensions. And also in this story, you can still talk about things like intersection number of splittings. So for now, I only need the following, that if alpha and beta, two splittings, two simple closed curves, so this intersection number is 0, so they don't intersect. They have a common refinement and non-zero otherwise. So For example, by this, I mean that this and this will have intersection number 0 if there exists some E, F, and G such that is bad, but H such that this is also isomorphic to G, and then A with B, and similarly. Yes,
Can you write twice as big?
yes, sorry. Um, Given an amalgamation, one can define an automorphism of the group, which will be the Dehn twist of that splitting. And in this case, the automorphism will be so T of alpha will be the thing which sends every A to A. And yeah, we got this as the thing generated by an MMC. And T of alpha of B will be equal to C V C in. With conjugation on one factor and the other factor stays in place. And in the case of an HNN extension, then T of beta on A is equal to A, and T of theta on this extra element T is A times, is C times T. Thing that I want to say is that it's also true in this situation that if two splittings don't intersect, then T of alpha commutes with T of beta.
You get different only if or
I'm presumably not, but not for every group. Yeah, other direction I think depends on the structure of the group.
Sorry, what is C here?
C is the generator of the cyclic group that you amalgamate over.
Isn't that beta?
Hmm?
Isn't that beta?
Beta is what I call the splitting.
Oh,
And it's not called thing. So yeah, now there's a bunch of things to do. First of all, well, I only described these things in the discrete world. To going to the pro-P world, first of all, to define amalgamation, then you take the push out in the world of pro-P groups, and it might not be the pro-P completion of this thing. And also I define an automorphism, not an outer automorphism. So I don't know, definitely don't know anything about the order of it. And so, yeah, for the rest of the time, I'll kind of explain for the Mushkin groups, what are their splittings over ZP and kind of how do you get that the Dehn twists associated to them are actually give you non-trivial outer automorphisms. Is concurrent duality group dimension 2, and also known as the Mushkin. And because P is not equal to 2. So first of all, these are, so this is a protein group with a contrariality of dimension 2. And the structure theory for these is that every such group has the following presentation. So it can be described as a free group on 2n elements mod a single relation. And so F2n is the free group on x1, y1, x and yn elements, and R is the group generated by the following relation that x1 to the p to the r, and the commutator of x1, y1, and commutator of xn and yn. And so every the Mushkin group depends on two things, the amount of generators and this extra power of P. And so for K over QP, with P to the S inside of K, and the maximal protein quotient of the absolute Galois group is the Mushkin. Okay,
Can you say what R and N are?
yes, sorry. Where R is decimals. Where R is so that the P to the R roots of unity are inside K, but the P to the R plus 1 roots of unities are not. And is equal to the degree of K over QP divided by 2 plus 1. The degree is even because P is odd and we have some P with QP inside. Okay. And so then to kind of look at what are all the ZP splittings, one can use the following. So there is also a relative notion of Poincare duality groups, which correspond to surfaces with a boundary. And in this setting, so G and S is relative to if where, so this is some pro-P group. And this is a family of closed subgroups. And the same subgroup can appear a few times. And so there exists a theory of relative group cohomology. And also of relative group cohomology for pro-P groups. And we want G relative to S. As a Poincare duality. And not only that, but Wilks fully classified relative Poincare duality groups of dimension 2. For discrete groups, any relative Poincare duality group is pi1 of a surface, with the family of subgroups being pi1 of the connected components of the boundary. And in the case of pro-P groups, then the classification is if S is equal to the family S0 SB. And then G is free. Well, assuming B is bigger. Well, yeah, assuming that S is non. So there is actually boundaries, and G is free of rank 2n plus B. And there exists a generating set of G and for x1, y1, xn, yn, s1, sb, such that si is conjugate to the group generated by si, and S0 is exactly the word x1 to the p to the r for some r. And using this, one also has that every splitting of a Poincare duality group gives you relative Poincare duality groups. So if G is equal to A, C, B, then A relative to C is relative EB2, and also B, and vice versa. So this already can give you a structure of exactly how they can look like. The question is, how do the invariants N and R change when you glue things? And vaguely the answer is you can always make something less orientable, but you can never make it more orientable. And if you do an amalgamation of two things, one orientable up to level R and R prime, then the result is the minimum R and R prime. Whereas for H and N extensions, you can take something completely orientable and glue it in a really non-orientable way, similar to how you can take a cylinder and glue it to be a Klein bottle. But because we can have that we have something here which is not orientable mod R and not orientable mod R prime, we get kind of more discrete groups that will complete to our Dumushkin group. So if we want to, so the method is to kind of, first of all, look at what are so maybe of fixed P and PD2 with 2n generator oriented mod P to the S, and then define the discrete group G R prime. So we have a family of discrete groups, which is the group generated by x1, y1, x and yn, such that x1 to the p to the r
Can you magnify the writing?
Huh?
Can you magnify the writing a little bit?
Yes, sorry. Yes. So this is the group generated by x1, y1, xn, and yn, with the following. So x1 to the p to the s. Where here R is greater or equal to S. And in fact, I was able to show that these family of groups have infinitely many non-isomorphic discrete groups in them. So you really do need to consider all these groups, because otherwise you would not get some of the Propi splittings. And then you look at kind of all the expected splittings, and by that I mean either kind of the free group on 2D generators amalgamated with the free group on 2n minus 2D generators. Where the word sphere is x1 to the s x1 until x d y is equal to x d plus 1 y d plus 1 until xn yn x1 p to the r. Similarly for H and N extensions, and then to make sure that so if I have such a splitting F2, F1 over L, and I want its Pro-P completion to be the same as Pro-P completing each one of the factors by themselves, then so to have this, we need to check that every such group theoretic splitting has the following properties that first of all, that the group GR is residually P, that it induces the full pro-P topology on F1, F2, and L, and that they are closed in pro-P topology. And from this, you get that you can pro-P complete such splittings, and so you get that there exists some map from Z splittings of this GR into by pro-P completing into ZP splittings of G, which is of GR equivariant. And actually that outer automorphisms act faithfully on split. But what essentially this means is just the following, that the outer automorphisms coming from Dehn twists on each of these groups GR embed into the outer automorphisms of the pro-P completion of them. And moreover, looking at okay, and then the main step to kind of and okay, so now what we need to do is to show that the Dehn twists are non-trivial for discrete groups, and to do that, one can use a very similar argument to how classically they are shown to be non-trivial, and that is the following. So lemma will show, but if for two splittings alpha and beta they do intersect, then so does the Dehn twist of beta with beta. And one more thing is that this intersection number, if you so which yes, and some kind of properties of this intersection number being invariant under conjugating any of the factors, and because each splitting does not intersect itself, then we would get that actually this is also true. That the Dehn twist can't be inner. Otherwise we would get here intersection number being 0. And then the game is to kind of for every such very specific presentation of a splitting to find another splitting which intersects it. But this again can be done by kind of what is it? Yeah. So for if you write down the generators and relations of group, then for a splitting which is separating, you take a splitting which will correspond to you need to write down the exact presentation of which will correspond to this, and for a splitting which is non-separating, you take this other curve which intersects it. And so kind of from all of this, you get that these Dehn twists also in the protein world will be infinite order, which gives kind of quite a big family of outer automorphism. And maybe we can also say that this outer automorphism constructed in NSW that I mentioned earlier. And so if I take, well, this is defined not on the maximal Propy quotient, but on the whole Galois group. But the Galois group is generated by xn, and what it does is it sends phi of sigma to sigma, tau is equal to tau, xi is equal to xi, except for phi of xn, which is equal to xn times xn minus 1. But choosing kind of the correct splitting, you can exactly get, I probably erased it, that this will correspond to the AGNN extension, the Dehn twist of the AGNN extension of the correct one. So this doesn't exactly include their example because I'm working with the Propy quotient, but this kind of has a similar flavor to Dehn twists. And I guess kind of future questions is first of all, what do these Dehn twists generate? Kind of everything topologically, maybe. I don't know. And also one can, as part of this, one can also define, this was also part of the work, and define curve complex. So the vertices of the curve complex are exactly the ZP splittings, and using whether or not they intersect, you can get like edges and faces. So you can have some curve complex on this, and I guess what is the structure of it? Classically, it's kind of known what its diameter is, it's known the connectedness, and maybe kind of more ambitious is to get stuff like Nielsen-Thurston classification. So kind of ones which are do not fix some set of curves to have some sort of dynamics into them, and get some dynamics on Galois representations, and kind of, yeah, after doing my PhD, I found out that a student of Jacob also did a PhD on something kind of very similar, where I think they took like completions of Dehn twists on an actual surface, but they also managed to get some stuff on the whole Galois group. But yeah, I guess that's kind of everything that I want to say.
So I just wanted to add the name. It's Teresa Kumfit.
Yes, sorry, I wrote it down and forgot.
Yeah. Yeah.
So, go ahead.
Okay, so I was wondering if you, I mean, here you think about only Poincare duality groups, but I mean, you know, for example, the Galois QP is almost a Poincare duality group. Like,
Yes.
so I was wondering if you allow like some kind of, you know, invertible dual, like Gornstein groups kind of.
Yes, so I have been meaning to write up, but I think that if you, I don't know how the relative version of like stuff like Koch formalism or that kind of stuff would work, but kind of one reason which I do think it should be able to extend, for example, Mochizuki's theorem can be restated by taking just the maximal pro-p quotient. And so kind of the non-p part is very small and shouldn't be affected by outdoor automorphisms. But yeah, you need to look at the slightly different formalism.
So concern is how is there anything to reality? So if you take a prime to P extension of the base field of K, maximal for P extension there, can you lift your dead twists to that? Because if you can do this for every prime, then you can lift them, and then you get out of what?
Yeah.
These become automorphic of that full about it. Yeah.
Yeah. Yeah. Look at that, but yeah, looking at like one step to find a BPM approach. Yeah, I guess that kind of is similar to kind of how it goes in the kind of Koch formalism where you look at like all the families of the Dehn extensions.
So that's
So probably something like that would work. And in a sense, I also think that QP can be thought of as like well, it should be like a relative duality group relative to exactly this extra one boundary relation, which will be I think in that case should be like x1 to the p, but basically the non-rentability comes from how many roots of unity are in the maximal Dehn extension. Exactly, if you look at the presentation of the whole Galois group and look at the quotient, you will actually see that you get a relation which kills one of the generators, which is why it's free, but that would mean that it's a relative duality group to that relation.
Other questions?
Yeah. So does this give you an interpretation on what the hot shade representations are?
So kind of that's another thing. So the idea here is that my hope, again, it's still work in progress, but now that you are able to, if you can classify which elements of the Galois group you can split over, then you can choose an element which is related to a very specific representation, takes a splitting over it, and then you know exactly how that specific Dehn twist at least changes things. So in that sense, that's kind of a potential answer of how to do it. Because now you can choose automorphisms which are related to a more arithmetic thing and not kind of a more abstract one.
So there's no classical analogy to the surface theory.
Of what Hodge state is, you mean?
Uh,
I didn't.
So you cannot say what does this construction with the filtration, with the ramification.
Yes, yeah, that would, again, I don't know. It would be interesting if there is something, because yeah, if there is some filtration you can put on it such that the outer automorphism group is it's finite or something. And I guess that also relates to this question that I was saying before, that kind of in the arithmetic topology picture, you're only accounting for like thinly ramified extensions, and so what is a row figure 8 not group or something.
No, concerning the comparison between the pictures. On the right hand side, the topology, you know, everything. What about global fields on the left hand side?
What do you mean?
So
Oh,
what about the picture of the maximal pro-p quotient of the absolute or the global field?
Ah.
Maybe of not of a number field.
it's not like it's like it is too much information, no?
I think that is rigid. I would guess that is rigid. I don't know. The guys in Anabelian geometry.
It doesn't determine that. Oh, do you mean?
There is no probability.
Yeah, but if the roots of unity,
You mean what is the outer automorphisms?
I don't sorry.
What would you,
But
not to reconstruct the whole global field.
it depends on the situation, so I forgot the
Maybe.
detail, but so such a result may be maybe proved by the student program or Tamagawa, maybe. Such a noise, so pro sigma, pro p by the noise, that is see that. But I'm sorry, I forget the detail. Anyway, still easy.
Okay, so let's answer guy.